All right, number 14. So 14 is really asking what coherent means. And coherent means that the waves are in phase, but they're in phase and then they stay in phase. And in order to be in phase and then stay in phase, the phase difference, first of all, needs to be constant at, let's see, do they need to be, they don't need to be, they need to have a constant phase difference. I was saying that they need to be in phase. They could be, I don't know that they need to be completely in phase, but they do need to have the same, a constant phase relationship, that's for certain. So definitely not a variable phase difference. And then if they're going to start in phase and remain in phase, then their frequency needs to stay the same, because if their frequency is different, then as the waves travel, they may start in phase, but then eventually they're going to shift out of phase since their wavelengths will be different. So the frequency would be the same and their phase difference would be constant. 14 is B. And that right there is pretty much the definition of coherence. Okay, number 15, we have a two-slit interference pattern. It says blue light is incident on two narrow slits. Constructive interference takes place along the lines labeled 1 to 5. So along those lines, constructive interference happens, which means those must be antinodal lines. So the blue light is now replaced by red light, so a different wavelength. What additional change is needed so that the lines of constructive interference remain in the same positions? So let's talk about those antinodal lines and really what's happening. So as that pattern happens, if I were to put a screen over here, what did it say, blue light? That means if I have the antinodal lines, what that's going to correspond to are the bright fringes that show up on the screen. And so then it says the blue light is now replaced by red light. And so for the two slits, the equation in question is going to be S is lambda D over D, where D is the separation between the two slits and S is on the screen. That's the separation from one bright band to another. There's S. And so it says the blue light's now replaced by red light. Now red is a longer wavelength, so that would mean that those bands would spread out. But then it says that what additional change would be needed to make those lines of constructive interference remain in the same angular positions, or in other words, in order for S to stay the same. So basically what happened was that by using red, we increased the wavelength, which would increase S, but now I want S to stay the same, so I'm going to need to do something to the distance to the screen or the separation between the slits in order for S to stay the same. So I can see that S and lambda are directly proportional. S and the slit separation are inversely proportional. So by increasing the wavelength, that increases the separation between the fringes on the screen. So I'm going to need, I can see that changing the distance to the screen is not an option, but changing the slit separation is an option. And so since I increased the fringe separation S by increasing the wavelength, I'm going to then make a change that then decreases the fringe separation so that the change is canceled. So I'm looking to decrease S, and so since S and D are inversely proportional, I would need to increase the slit separation to move the slits further apart. That leaves me with choice D. Okay, number 16. Monochromatic light is on a double slit. Slits of a finite width. The light then forms an interference pattern on the screen, which shows the variation of intensity with distance from the center of the pattern. This is on two slits. And A looks good. We have the peaks and troughs. We have the constructive interference and destructive interference alternating. So A looks good. However, we also have to recognize the envelope caused by single slit diffraction, where there's a large central peak and then there are smaller peaks to the side. B looks good, except that the peaks to the side are the same height as the central peak. That's not going to happen. So we don't have A, we don't have B. C has the right envelope, but I don't really know what's happening in the middle. I don't know why, I don't know where the interference pattern happened in the middle. Our answer is choice D. We have the interference pattern caused by the two slits, but that interference pattern is modulated by the envelope caused by single slit diffraction. So 16 is D. And then last but not least, for the multiple choice, we have this guy here by itself, and it's talking about a diffraction grating. And it says, what's the greatest number of maxima that can be observed using the arrangement? So it wants to know which, based on the slit separation that they gave, what is the greatest number of n? And so the way we figure that out is we set theta to 90, and then whatever we get for n, we take the largest whole number under that. Because 90 degrees is, again, or rather the angle, I should say, when we're talking about like the diffraction grating, and then we have the screen, and then there's the center line. We're talking about this angle here, that goes to all of the different maxima. It's like n equals 1, n equals 2, n equals 3, fourth maxima, 5 maxima. But then as that angle increases, basically once you hit 90 degrees from the center line is definitely not going to hit the screen. 89 degrees will, barely, but 90 definitely will not. So if we set theta to 90, whatever n is, we know that right under that will hit the screen. And they gave us a slit separation of 7 lambda over 2. All right, so we know that d is 7 lambda over 2, and of course the sine of 90 degrees is 1, and so we're left with n equals 7 lambda over 2 divided by lambda. That leaves us with 7/2. And so that's the 3.5 order. Of course, n is a whole number, and so the smallest order that we can see is n equals 3. Oh, wait, no, I'm sorry. No, that's 3.5 on one side. I have to account for the other side as well. So that's 3.5 kind of like looking at the illustration of the screen, the setup I did right here. That angle is from the center line going up. I also have to consider the angle kind of going the other way. So from one side of the center line, it's 3.5. I also have to consider the other side of that center line. That's another 3.5. So altogether, that makes 7 orders in accounting for both sides of the center line. And so that is choice C, which makes sense because 3, which was my original guess, is not an answer. So, but now I was only accounting for one side. I'd have to double it up. So 3.5 doubled up makes 7, which is choice C, and that's what the mark scheme says. So ta-da, all done. All right, and that was the end of the paper 1 questions that QBank had found on 9.3. Okay, so I just imported all of the paper 2 questions, starting with number 8. And, whoa, what happened? I've lost everything else. Oh, nope, there they are. Whoa, how'd they get so small? All right, now let's make them bigger. There we go. All right, make them a little bit bigger. And so I'm going to get those into place. Let me stop recording and fix it. There we go. That's better. So now, oops. There. All right. Let me actually pinch the page to zoom in. Nope, I don't want to do that. Okay, showtime. Now we have number 8. We're going to look at 8A through 8E. So 8A wants us to explain how a dark fringe is formed. A dark fringe is formed from destructive interference. So yeah, the dark fringe is destructive interference. The source waves are 180 degrees out of phase. A crest is meeting a trough, I guess you could say. So the path difference between the two slits, from the top slit to the spot on the screen, and from the bottom slit to the spot on the screen, that difference in their paths has to be an integral number of half wavelengths to have the destructive interference. For some reason in the mark scheme, it says ignore any reference to crests and troughs. I don't really know why. You can think of phase difference in terms of crests meeting or troughs meeting or crests meeting troughs, but really, if you're going to talk about phase difference, you really should be talking about the angle, either in degree or in radians, the angular difference. And so if you're completely out of phase, it's 180 degrees, completely out of phase, or pi radians. Okay, 8b says, why does the beam have to be coherent? What does coherent mean? All right, so 8b, coherent means in phase and same frequency. So the interference pattern that's produced on the screen, like the fringes that we see, only occur on that screen if the light waves coming out of the two slits, the two sources, are the same frequency. That's what you mean by monochromatic. There's only one frequency, and they're in phase with each other. You still get an interference pattern if the light waves are not in phase, but that pattern doesn't look the same way on the screen. You don't get the fringes that you would otherwise. All right, so this is, and really, S equals lambda d over d is not an HL topic. You learned that in SL, but it's so relevant to double slit, we might as well, like, you can't avoid it, right? You can't be like, oh, we already did that, we're not going to do that now. It's so ingrained in double slit. So here we are, and now it says the separation between a dark and bright fringe on the screen is 4.5 millimeters. S, the separation of the bands of the bright fringes on the screen, that's not from dark to bright fringe, that's from bright fringe to bright fringe. So not to worry, it says that from a bright fringe to a dark fringe is 4.5 millimeters, which means that the distance from a bright fringe to the next bright fringe is double that. So otherwise we're solving for the distance to the screen using an S not of 4.5 but of 9 millimeters. And we wind up with a distance to the screen of 4.27 meters. Also, the distance between the slits was given at the beginning of the problem. Distance between the slits is 0.3 millimeters. That was at the description right up here, right there. Okay, let's find 8D. We have ourselves a diffraction grading pattern. Okay, so 8D is making reference to a missing peak, and the reason why that peak is missing is because of the envelope caused by the single slit diffraction pattern. That's the dotted line that we see. So that's kind of worth noting and definitely relevant to 8E. And the peak that's missing is the fourth order peak, where the center peak is 0. And so we have first, second, third, and then that missing peak would be the fourth order. And even though this is two slits, we're going to use the diffraction grading equation, which really refers to multiple slits. So this is just two slits, but whatever. We'll use d sine theta equals n lambda, and we're going for theta. All right, so theta would be sine to the -1 of n lambda over d, and n is 4. Lambda was given 633 nanometers. The separation of the slits d is 3 millimeters. Let's solve for theta. I'm listening to my solutions here and realizing that the separation is 0.3 millimeters, not 3 millimeters. Let's see. And my solution shows that, but that's not what I actually said. 0.3 millimeters. Anyway, so when we do 4 times 633 times 10 to the -9 divided by 0.3 times 10 to the -3 and take the inverse sign of that, you can be in radian mode or degree mode, it doesn't matter. They'll accept either answer. But in radians, it's 0.00844 radians or 0.484 degrees, very small angle. Okay, let's take a look at 8E. Deduce the width of one slit. See, now that's interesting. The width of one slit, the slit width, the only formula that actually gets into slit width is the single slit diffraction equation, that theta is lambda over b. Lambda, of course, is wavelength, b is the slit width, and theta is the angle from the center line to that first minimum. It's pretty much half the width of that large central envelope. Using the diagram that they gave us up here, theta would be from the center line to where that first minimum is the width, half the width of this envelope. So that right there would be theta. It just so happens that in 8D, that's the same angle. When they're talking about what's the angle to the fourth order maximum, which is actually, it says the missing peak that should be there. And the reason why it's missing is because it lands right smack where the first minimum is from the single slit diffraction envelope. So the angle that we solved for in 8D, that angle that we solved for in 8D is the angle for this single slit equation. So I can just use that. I'll use the radian answer. I know what wavelength is, and now I can solve for B. And we get that the slit width is 7.5 times 10 to the negative 5 meters. It does say in the question to get the answer in millimeters. This says nothing in the mark scheme. What if you gave the answer in meters? It just says allow ECF. Whatever, we can convert from meters to millimeters, getting us 7.5 times 10 to the negative 2 millimeters for one slit. And I believe that's all. We're not doing 8F. Relative motion of the galaxy and the Earth. That is a Doppler effect question. We're not going there just yet. All right, let's take a look at 9A. So we have two lamps and a screen. So they're not slits, but they are two sources. And we can go from there with that. So in this example, we have two sources, but they're not point sources. They're just kind of two lamps. So we're not going to get an interference pattern like we would from two slits. We're just going to get the combined influence of the two lamps. And it says that each lamp has an intensity of I naught, and we have two of them. So the intensity for this graph would have a maximum of 2. Let's zoom in on that. Would be at around 2. And then the mark scheme says you could just kind of have like a straight line at 2. I would say that as you move away from center, you are increasing distance slightly away from both of the lamps. I would say maybe it should be curved a little bit. The mark scheme does allow for that. So maybe a little something like that. But definitely on the center line, having a intensity of 2. Now, if we go to the next question, here's 9B, and in 9B, they've then replaced the two just lamps with slits. So now we're getting an interference pattern, but we still have two sources, and so we're taking that intensity of the average, pretty much the average intensity of 2, but we're now making that into a series of crests and troughs. So, it's basically 2 being the average, where the trough has no intensity and the crest has maximum intensity. So if we follow that pattern, then it's going to rise to 4, the height of the peaks. And it rises to 4 because 2 is the average of 0 and 4. And of course, we need to get the width of each maximum, of the width of each peak. And of course, we need to get the position on the screen, so we need to get the little s being screen, the distance from the center maximum to the n equals 0 maximum to the n equals 1 maximum, and that's 2 centimeters. And so I've kind of sketched out the relevant points, so if I connect them, there we go. It does say in the mark scheme that you can also control for the single slit diffraction envelope, but it's not actually required among the 3 marks for this problem. Just as a little addendum to this, the mark scheme says that this interference pattern as shown in my solution is sufficient, but it also kind of bothers me that it's not modulated by the single slit envelope. And so I'm just trying to figure out, like, what is that theta representing the angular position of the minimum created by the single slit envelope. And that theta is lambda over b, where b is the slit width, and the problem doesn't actually give the slit width. So it's actually not possible to account for the single slit diffraction envelope, because I have no idea what b is. And so this pattern, as shown, is without considering the effects of the single slit diffraction. Anyway, moving on to 9c, it says slit separation is increased. What is one change observed on the screen? Slit separation, of course, is represented by little d. And it says that the slit separation is increased. And so one change that would occur, it's not going to change the distance to the screen or the wavelength, but I can see that little d and s, that's the distance on the screen from maxima to maxima, that would decrease, and so the maxima would get closer together, the fringes would get closer together. And one other thing that they include in the mark scheme, which makes sense, is that you can see more maxima. If the fringes are closer together, then you can see more of them. And there you go. And that's the end of number 9. And 10a through 10d is the last problem on this assignment. The other guys, I guess, do not deal with 9.3, but let's start with 10a. So, yellow light from a sodium lamp of wavelength 590 nanometers, incident at normal incidence on a double slit. Here's the interference pattern, and it's shown why zero intensity is observed at position A. Okay, so we have this pattern here. It says zero intensity observed at position A, and I can think of 2 reasons why there's zero intensity at position A. I can see that there is the double slit diffraction pattern shown, and A seems to be, if you zoom all the way in, there it is, you can see that A is in between 2 maxima as caused by the double slit pattern. So that's one reason why there seems to be zero intensity at position A, but I don't think that's what they're getting at. I will put that down. But I think what they're really getting at here is that the zero intensity is caused by the single slit diffraction envelope, which, when we look at the main pattern, here's the primary maximum and the secondary maxima caused by the single slit diffraction envelope, and so that point A corresponds to the minimum of that. And I think that's what they're really getting at in 10A. But that's kind of 2 reasons why there's zero intensity at position A. There are 2 marks in this answer. They don't actually want both answers, but the 2 marks correspond to some recognition of interference occurring, particularly destructive interference, and then also some recognition of the single slit diffraction envelope that should be mentioned. So I guess in that sense, really, they kind of do want both answers. I don't know, but anyway, that's 10A. So 10B wants the width of each slit. There's only one equation that talks about the width of a slit, and that goes back to 9.1, which is the single slit diffraction pattern, and we know that the angle from the central line to the first minimum is theta is lambda over b, and so A is actually at that first minimum, so that, that angular displacement from center line to A is theta in that equation. And so theta is lambda over b, so b, what we're looking for, is lambda over theta. And of course, for small angles, tan theta is approximately equal to theta. So we get 0.0058571429 for theta in radians. So we can use that, and then the wavelength was given somewhere, 590 nanometers. That was given in the description of the problem. And in the end, after we figure out that angle and we solve for b using the wavelength they gave us, we get 1 times 10 to the negative 4 meters, or 0.1 millimeters. Okay, so 10c wants the separation of the two slits, and the mark scheme says to use s equals lambda d over d with 3 fringes. I think it makes more sense to use the diffraction grading equation. N lambda equals d sine theta, where theta actually corresponds to the third maximum. Let me explain that. So here's the diagram, and so we have the primary 0th maximum in the middle, and then we have maximum 1, 2, and then 3. Now there would have been a peak here, except that that peak gets squashed because that also corresponds to the minimum point caused by the single slit diffraction envelope. But that point right there, A, does correspond to the center of the maximum of the n equals 3 maximum. So I already know what that angle is from the center line to point A. That angle right there, which is also the angular displacement to that third maximum. And so we actually solved for that theta over here, where we said theta is approximately tangent to theta because of very small angles, and so we actually have a value for theta. That value for theta is right here. And so what we're looking for here is actually d, where n is 3 for the third order maximum. So we can stick that in for theta. And so we wind up with a slit separation of 3 times 10 to the negative 4 meters, which does correspond to the answer key. And so don't forget that you can use the diffraction grading equation for multiple slits with only 2 slits. It still works. Finally, we have 10D, and it says double slit is replaced by a diffraction grading that has 600 lines per millimeter, and the resulting pattern is shown. So we have many more lines, much more than 2, and so we can see that the peaks get tighter. The spaces between the peaks get bigger, and the peaks themselves get tighter and more intense. State and explain the difference between the pattern on the screen due to the grading and the pattern due to the double slit. So yeah, increasing the slit count allows more light to each, so each peak intensity increases. Also, the peaks become more narrow as the slit count increases. And then finally, since there are more slits per unit area, the slit width decreases. So that's like theta is lambda over b. So if b is going to get smaller, then theta gets bigger. And so that diffraction envelope is actually broader as a result. And that is that. That was 10D. We're not going to do 10E because that deals with resolution. And then there's the other questions down here that we're not going to get into. And so 10D is the last one we're looking at. Thank you very much.